Rearranging equations is a fundamental skill across mathematics and physical science. Frequently our models are described using equations, but we will almost never have the equation in the form that we need, requiring us to rearrange to make a particular value the subject of that equation. Sometimes these rearrangements are trivial, sometimes they are trickier, but we find that students struggle with the more advanced rearrangements, so it's worth us devoting some time to make sure the concepts are firmly in place. Consider the following equation, a fairly straightforward one. 3 plus 4 equals 7. Again, here we are simply stating the symbols, but translating it into our more common language, the value you get when you add the value 3 to the value 4 will be the same as the value of 7. This tells us what the equals sign is doing. It's simply making a comparison, saying that whatever is on one side is the same as whatever's on the other side. Basically, 3 plus 4 is the same as 7. What if we wanted to rearrange this to keep the same values of 3, 4 and 7, but we wanted 3 alone on one side? Most would say, swap the side, swap the sign. This approach works for addition and subtraction, but it doesn't work for higher order operations. So let's look at it another way. For the equality to be preserved, we have to do the same thing to both sides. If we just randomly subtract 4 from 7, it will not be equal to the left side of the equation. Therefore, we have to subtract 4 from both sides. On the left-hand side, the 4's cancel out, and we end up with the statement that we wanted to find. This basic principle applies to all rearrangements. Whatever you do to one side, you have to do to both sides in order to preserve that equality. A key equation in chemistry is the Gibbs equation. The change in Gibbs energy is equal to the difference between the enthalpy change, delta H, and the entropy change at that temperature, T delta S. If we wanted to make the enthalpy change, delta H, the subject, what do? We can see fairly quickly that we want to take the T delta S over to the other side, but how do we do this in the method described earlier? Well, we simply add T delta S to both sides, and on the right-hand side this will cancel out. This gives us the equation we were after, isolating delta H, which is now equal to the sum of the Gibbs energy and the entropy change at that temperature. What instead if we wanted to isolate the entropy term, S? This requires a bit more jiggling, but the steps are straightforward. Let's start with the delta H equation we created, but now let's subtract delta G from both sides. This isolates the T delta S term. As there's now a multiplication on the left-hand side, we need to use the inverse operation, a division. So we divide both sides by T, and this then isolates the S term. We are taking methodical steps, making sure we only do one step at a time. It doesn't matter what order we take the steps in. Provided we are methodical, we should get the same result. Another rearrangement we should be able to do in chemistry is that of the Arrhenius equation. Students of chemistry again will readily recognise the form of the decaying exponential, relating the rate constant K to the activation energy of the reaction EA. Rearranging this equation is again straightforward, however we need to be methodical in what we do. Firstly, we divide both sides by A. This allows us to isolate the exponential. We then need to use the inverse operation to undo the exponential. Remember, in this case, we use a logarithm with the base of e, the natural logarithm which carries the symbol ln. So, let's take logarithms of both sides. As we said before with operations and their inverse, a logarithm of e to the power of a value simply returns the value. So we obtain minus ea over rt. Now it's simply a case of multiplying both sides by rt to get the final statement of the activation energy ea. There are many tips and tricks for rearranging equations which we'll discover as you go through your studies. However, there are 3 basic steps to successfully rearrange an equation. Only do one step at a time. This is a frequent source of error where a student tries to do too many steps at once and makes mistakes. Whatever operation you do, you must do it to the entirety of that side of the equation. You can't simply pick a term on one side and only do it to that term. And finally, whatever you do to one side, you must also do it to the entirety of the other side of the equation also, to preserve that equality. Once you've performed an operation, you can then see what cancels out, and hopefully that takes you closer to the term you wish to isolate. Rearranging equations is an essential skill in physical science, and it's important to practice this if you're not confident. An incorrectly rearranged equation can lead to bigger problems further on in your studies. Our next video will start to use the ideas introduced in our first few videos and apply it to geometry in a chemistry context. Do continue to ask questions and post comments below if anything's not clear, and as ever, see you next time.